Hey guys, Miss Peterson here, and welcome to AP Physics 2, Lecture 13-3, all about lenses. Here we're going to be going over converging lens and diverging lenses. This goes with our converging lens lab, and I highly recommend you check out the physicsclassroom.com concept builders for lenses. They'll be super great practice. So, lenses, work on refraction, okay? Mirrors work based on reflection. Lenses are very similar, but they work on refraction. And we have two general types of lenses, okay? Where when the lens is thicker in the middle, okay, and it makes light rays converge, we call it a converging lens. Okay, and you can see from the shape, both sides of it are convex. So sometimes you'll see it called convex. Where if the lens is thinner in the middle, then it's going to make the rays diverge that go through it. So we call it a diverging lens. Okay, and it has concave sides normally. Now, just like our mirrors, we have sign conventions for these. For converging lenses, they will have a positive focal length, just like converging mirrors. And for diverging lenses, they will have a negative focal length, just like diverging mirrors. So again, positive F for converging and negative F for diverging. But the object distance is a little bit different, okay? So for the object distance, it's going to be kind of opposite of mirrors. I like to think of it as if we have a positive object, the object distance is always going to be positive. Okay. Boop. Now, for our image distance, it's a little bit different, okay? We will have a negative image distance if it's on the same side as the object, okay? And a positive image distance when it's on the opposite side. I tend to think of it as it's positive if it's kind of where you expect it to be. When we look at a mirror, we expect the image to reflect on this side, so that's the positive side. But if I'm looking through a lens, like my glasses here, I expect the images to be on my eye, on the opposite side of the lens. So that's defined as the positive side for our images. Okay. Now, we're going to be drawing ray diagrams for these, just like we did for our lenses. And they're going to be pretty similar. Incident rays that go parallel, okay, will refract through the focal point. Ones that go through the focal point will reflect parallel. And we have that optional third ray going through the vertex. Okay, so also we have to remember that we use the positive focal length for converging lens and the negative focal length for diverging lens. So let's go ahead and see how this works a little bit with a PhET simulation before we draw some ray diagrams. Yep. Whoop, whoop. So this is the geometric optics PhET simulation. We have our lens here. We can control its index of refraction, okay? When you have a higher index of refraction, that's going to diverge or converge the rays more. It's going to change the direction more. Okay, and we can see that these rays go through and converge to form that point. If I added a second point here, we know that this is happening along every part of the image, okay? Just because we draw it from the top to help us locate it, it's still happening everywhere along that image, okay? So we see that converging rays, we can see it with many rays, how they form that image. And for diverging. Yep. Start to see some of these patterns. Let's go ahead and draw them ourselves. we're gonna start with this first one. Grab your rulers. And like lenses, our first ray is going to go parallel and then refract through the focal point. Where rays that go through the focal point, okay, we draw them through the near focal point, will refract parallel. Okay, so we can see our image there. And then that optional third ray goes straight through the vertex. So that one would be like that. Now, so we can see for a converging lens, if our object is between F and C, we're going to have an inverted, reduced. It's formed from converging rays, so it's going to be a real image located between F and C. Okay. Let's go ahead and try the next one. So let's go ahead and try it for this next one. We start with the parallel ray, and it refracts through that focal point. And we draw one that goes through the focal point and refracts parallel. Okay. And then we can always draw an optional third ray. Oop, my ruler's messing with my screen here. Going through the vertex. So we have an image about right there. Okay. And it is still inverted, reduced, and real. And let's see if it should actually be a little in front of the focal point, or as that object gets farther away, does it approach the focal point? Let's check it with the simulation. Okay, so we can start with that object near the focal point, and our image is going to be way far out there, can't see it here. And as that object gets farther away, yep, our image approaches the focal point. Okay, you can start to see things are going to get a little different when we get in front of that focal point. So let's go ahead and draw one of those ray diagrams. Okay, so we're still doing a very similar process. Okay, we're going to draw the ray that goes through parallel and refracts through that focal point. And then you can see where this is going to get funky. If we're drawing one coming from that near focal point, we're going to have to line up our ruler so it's at the tip of the arrow and the focal point. So we end up with a line something like that. Okay. And it is going to refract parallel. Now, these rays are diverging, so they're never going to form an image. But remember, our brain doesn't know that. Our brain assumes they all came from somewhere behind. So let's trace these images back, these refracted rays. Make sure you're tracing back the refracted rays, not the initial light rays. And we get our image right there. Okay, it is now magnified. It's formed from those diverging rays, so it's a virtual image, and it is upright. This is how a magnifying glass works. Okay, cool. Okay, cool. Let's go ahead and do some for diverging mirrors. Okay, so for diverging mirrors, very similar process, okay? Incident rays that come parallel to the axis will refract as if they came from the near focal point. So we're kind of switching our focal point references between converging lens and diverging rays. Ones that go toward the far focal point will refract parallel. And again, we have that optional third. So let's see what this looks like. So we have one that seems as though it came through that near focal point. And it is going to, oh, I should draw the, oh yeah. Shoop, this is a converging. So let's start with the parallel one. And again, it refracts as though it came from the near focal point. So you're going to line up your ruler with where that ray hit and that near focal point and draw that diffracted ray. Okay. Then for the second one, you're going to line up your arrow going toward the far focal point. Okay. Instead of going through the near one, you're going through the far one. Okay. You go toward it and then it refracts parallel. They're diverging rays, so we got to trace them back. And we'll trace this refracted ray back. Okay, and we get a little tiny intersection right there. Okay, and we can see, we can always check it with that third ray. If you're not feeling confident on your image location, just draw that third ray, and it should help you pinpoint it a little closer. Yep. So let's do one more of those type. So we go parallel. We diverge as if we came from that near focal point. We go toward the far focal point. And we refract parallel. We trace the rays back as best we can here. Okay. And we can see that diverging mirrors are pretty much always going, or sorry, I said mirrors, lenses, diverging lenses are going to make reduced, upright, and virtual images. Okay. And we can check that in the simulation. Always a good idea. Throw on the diverging lens, and no matter where we have our object, we are going to have the similar type of image. Okay, cool? Okay, cool. So let's talk a little bit about why I'm wearing these glasses, okay? So we have two things acting as lenses in our eyes, okay? Both the cornea of the eye, this part, and this part right here. However, the most important part of that is these ciliary muscles. Those are these guys, okay? Right here. You can see that muscle fiber. They contract and they change the shape of this lens, which determines where the image appears, okay? Now, we want the image on the back of our eye, on our retina, okay? But if the muscles are too contracted, okay, they're diverging it too much, well, how are we going to fix that? Okay, that image is showing up too close. So if we put a diverging mirror here, that would cause these rays to spread out a bit before they hit the eye, and thus refract at, that's ugly, okay. If we add that diverging lens, it would allow these rays to refract a bit before they hit the eye, which would spread them out and allow them to be better focused on that retina. Okay, where if you have that far-sighted situation, okay, if that image is focusing behind the retina, we could add a converging lens, which would bring these rays a little bit closer and fix that image location. Okay. Yeah, so reminder, nearsighted is when you have trouble seeing far. And farsightedness is when you have trouble seeing near. So your muscles have trouble contracting enough to bring that focal point to the forefront. Or nearsighted, your muscles tend to contract too much and bring that image too closer. Okay. Let's go ahead and do some problems using the math. Hey, wait a minute. Have we talked about the math for lenses yet? Nope. But yes, The math for lenses is the same as the math for mirrors. So we're still going to be using the equation 1 over f equals 1 over the image distance plus 1 over the object distance. We just have to be careful with our new sign conventions. Okay, so we have an object with a height of 11 centimeters, which is placed a distance of 44 centimeters in front of a converging lens with a focal length of 24 centimeters. Locate and describe the image. Okay, well, let's go ahead and start with a quick little sketch of what's going on here. Here we have our lens. We have a focal length of about 24, and then our object is at about 44. So not quite at 2f, but pretty close. So I'm just going to draw it right there. I'm going to do a very rough sketch of our rays here. We would go parallel and refract through that focal point, and we would go through that focal point and refract parallel. So I'm guessing that image should be somewhere between f and c, 2f. But let's go ahead and calculate it out. We'll have 1 over 24. The image is on the opposite side, so that is the positive side. Our object distance is always going to be positive for lenses, so we just have that 44, and we're solving for the image distance. Okay, go ahead and grab my calculator. So I have 1 over 24 minus 1 over 44, and then I take the inverse of that, 1 divided by that answer, to get an image distance of 52.8 centimeters. Okay. So then if I want to find the height of the image, remember our equation is that the image over the object equals the height of the image over the height of the object. And we use absolute value signs for these ones. So I got 52.8 over 44 equals the height of the image over 11. And so 52.8 times 11 divided by 44 gives me 13.2 centimeters. Okay, a slightly enlarged image, which is to be expected when I have that's a little weird that I got a bigger image height than our object height. Is that possible with a converging lens? When in doubt, check the simulation. We'll go to that converging lens if we get a little closer. Oh yeah, okay, that definitely looks like it might be a little bigger. Wondering if this one maybe should have been a little bit larger. We have a focal distance of 80, so 160 would be where C is. So I'm going to line that up here. So if I have this in between F and C, okay, even if we're out at C, yeah, looks like we have a slightly taller image there. So let's fix that in here, okay? Hard to draw accurate ray diagrams. It is inverted, but it should be magnified. Okay. So let's go ahead and try this one. This time we have the same height, 11 centimeters, placed 48 centimeters in front of a diverging lens. That's why we have that negative focal length of 24.5 centimeters. Let's go ahead and draw our quick sketch. Okay, and it's at 48 centimeters, so it's almost exactly at 2F. Quick little sketch. Again, we go parallel. We refract as if we came from that near focal point. We go toward that far focal point. We refract parallel. And then we trace them back. And we expect an image about like that on the same side of the lens. Okay, so a negative image distance. Let's go ahead and do the math. We got 1 over negative 24.5 equals 1 over 48 plus 1 over our image distance. So negative 1 over 24.5 minus 1 over 48. Take the inverse of that, and we do indeed get a negative number. Okay, we get an S image of negative 16 centimeters, which makes sense. It's in front of the focal point as our drawing suggested. Let's go ahead and solve for its height. We will have, remember their absolute values, so we just have 16 over 48 equals the height of the image, which is what we are looking for, over 11. So we have 16, technically this was 16.2 times 11 divided by 48 to get an image height of 3.7 centimeters, a reduced image, which is also what we expected. And that's it for lenses. Okay, cool. Okay, cool.